So for this module, we are going to have a deep dive on explanatory AI, or XAI. So understanding not just what AI systems predict, but why they predict it. So on this slide, I outline our roadmap for the discussion and our goals as well. We will explore why explanation matters, building user trust, satisfying regulations like EU AI Act, and enabling efficient debugging when models misbehave. Research by organizations such as McKinsey and others shows that explainability reduces deployment failures and audits friction, supporting responsible AI development. Next, I'm going to clarify the difference between glass box models, which are inherently interpretable, and post hoc explainers, which brings transparency to more complex black box models. You will learn methods such as SHAP or LIME tools, developing purpose-built UIs for explanations and understanding ethical and regulatory thresholds. Now that you understand where we are headed, let's begin by unpacking two fundamental concepts. Isn't interpretability the same as explainability? Well, you will see they are distinct, but both are vital. So here we clarify an important distinction: interpretability versus explainability. Terms often used interchangeably, but meaningfully different. Interpretability refers to the intrinsic transparency of a model itself. Think simple models like linear regression or decision trees, where you can inspect weights or rules to understand decisions. These are glass box by nature. Explainability, on the other hand, is a post hoc construct. It explains the behavior of a black box model, like a deep neural network or ensemble, after the fact, helping you understand why a specific prediction occurred, even though the internal logic is complex and opaque. The EU AI Act explicitly mandated that high-risk AI systems must provide meaningful information about the logic involved and decision pathways. This means it's not enough to issue a prediction. You must explain it. From a practical standpoint, explainability accelerates debugging and builds trust. If an AI model in finance denies a loan application, sharp methods such as sharp scores might reveal it relies disproportionately on a zip code feature, a fairness concern. Explainability makes such problems visible and fixable, reducing audits, non-compliance. So while interpretability is about simple, transparent models, explainability is about translating black box decisions into human understandable rationales. With that in mind, let's map the broader XAI technique landscape. What methods exist and when to choose which one. Next, we will position methods such as SHAP, LIME, and other techniques with a global versus local and model-specific versus agnostic framework. So this slide situates explainability techniques along two dimensions, global versus local, and model specific versus model agnostic. Global explanation includes usage for overall feature importance. So it reviews model behaviors across the entire data set, useful for audits or regulatory reports. And local explanation focus on why a model make a decision for a single instance, crucial for supporting individual decisions, such as why was this loan denied. Model-specific method like SHAP's tree explainer or integrated gradients in PyTorch tap into the internal structure of a model for accurate attribution. Model agnostic methods such as LIME or permutation importance work with any model via input-output sampling. The toolkit ecosystem includes SHAP that provides consistent attribution for various model types. LIME offers intuitive local surrogates explanations. Interpretable ML is about exploration, glass box models, and global explainers. So choosing which tool to use depends on your data type, such as is it structured data like tabular data, or is it unstructured data like text or image data, your latency and compute constraints, and whether you need provable compliance with explainability standards. Now let's dive into SHAP specifically, its game theoretic foundations and why it's so powerful. Next, we will explain how SHAP works and what makes it attractive for both global and local explanation. So here we examine SHAP short for sharply addictive explanation. Grounded in cooperative game theory, SHAP employs Shapley values to distribute credits among features for a prediction, ensuring fairness via properties like additivity and consistency. SHAP offers variance explainer tailors to model types, tree explainers for tree-based methods, kernel explainer for any model, and deep explainer for neural networks. The strength of SHAP include providing both global and local explanation, aggregation across data, and per-instance attribution. And it also offers consistent attribution across features and models, which aids auditability. And it handles feature interactions in complex models. However, computational cost can be high on large dataset, especially with kernel explainer, and attributions assume data independence, which may be violated in highly correlated feature sets. A recent biomedical case shows both SHAP and LIME are sensitive to feature collinearity and may misattribute importance if not handled carefully. Still, SHAP provides transparency and consistency that few other methods match. So this is a concise SHAP Python example you can run immediately. We import SHAP library and train an XGBoost classifier on our training set. We then instantiate a tree expander. This is optimized for tree model and efficient. We compute Sharp value for our test set, which yields feature contribution per instance. Finally, we call summary plot, which produce a global overview, a bar chart of feature importance, and a swarm plot reviewing the sign and distribution of effect across instances. Frame the result for think of in the way that the visual output shows which feature most influence predictions, such as age, income, and whether they push the model output higher or lower. It's interpretable to both practitioner and domain experts. And also, please make sure to keep Sharp version up to date to ensure compatibility and improvement in tree expander. Also, the choice of baseline, such as average prediction from training data, affects interpretability and consistency of results. So let's dive into the technical underpinnings of Sharp. So it's a powerful method for interpreting predictions from any machine learning model by assigning an importance value to each input feature for a given prediction. It's rooted in cooperative game theory, specifically the concept of Shapley value. Imagine our model's prediction on the payout of a game and the input feature as players. A Shapley value for a feature represents its fair contribution to the prediction. This fairness implies two key properties. A feature's contribution is based on its marginal impact, and this impact is averaged across all possible orders or permutations in which features could have been introduced to the model. Technically, for a given instance and a model, Sharp aims to explain the predictions by computing a contribution value for each feature. These values represent how much each feature contributes to the difference between the actual predictions for that instance and the average output of the model across the entire data set. So here's how a feature's contribution value is determined. For each feature, its Sharp value is calculated by considering all possible groups of other features. Within each group, we measure the feature's marginal contribution, that is, how much the model's prediction changes when that specific feature is added to the group. This change is then averaged across all possible order in which the feature could have been presented to the model. This exhaustive averaging ensures that the value assigned to each feature is truly fair and accounts for all possible interactions with other features. The magic of Sharp lies in its additive nature. The final prediction for any given instance can be precisely reconstructed by starting with the model's average prediction over the entire data set, and then simply adding to the individual Sharp contribution value of all the features for that specific instance. This means each feature's impact on the prediction is clearly broken down. Sharp values possess desirable properties like local accuracy, meaning they accurately reflect the model's behavior for the specific predictions. They also ensure that features that truly have no impact are assigned zero importance. And if a feature's actual influence increases, its assigned importance also increases. While the exact calculation is complex, SHARP provides optimized versions such as Tree SHARP for tree-based models and kernel SHARP for general black box models, making it computationally feasible even for large data sets and complex models. Now let's unpack LIME, which stands for Local Interpretable Model Agnostic Explanation. LIME focuses on local behavior. For one instance, it perturbs input, build a sparse linear surrogate model, and attributes weight to feature to approximate the black box local decision landscape. So its advantage includes its model agnostic nature. It can work with any model while input-output sampling. It's intuitive and fast. Agents or domain users can quickly understand feature influence for a single prediction. And it's also flexible. It applies equally across tabular text or image domains. Its weakness is that it's inherently unstable. The repeated runs can yield different explanations due to random permutation, especially at low sampling size. Studies such as recent studies highlights LIME's inconsistency across replications, particularly on text data. Its explanation quality depends on choice of kernel and sample counts. Fidelity may falter near decision boundary. It provides only local approximations. Global model behavior remain opaque. So now let's have a deeper delve into this technical process. So LIME begins by creating a new local data set of synthesized samples. This is done by randomly altering the original input instance we are trying to explain. For structured data like tables, this might involve slightly changing numerical values or randomly selecting different categories for categorical features. For images, LIME might selectively turn parts of the image, like superpixels, on and off. For text, it might randomly remove or replace words. Each of these newly generated, slightly varied samples is then fed into the original complex black box model. The model produces a prediction for each of these perturbed samples. Then we will do proximity weighting. LIME then calculates how similar each perturbed sample is to the original instance we are explaining. A special function is used to assign a weight to each perturbed sample. Samples that are closer or more similar to the original instance receive higher weights, while those further away receive lower weights. This step is crucial because it ensures that the local explanation prioritizes being accurate to how the black box model behaves just right around our specific instance. And then local interpretability model training. So LIME trains a simple, inherently interpretable model like a straightforward linear model or a very small decision tree on these new local data sets. This training uses the perturbed samples, their predictions from the black box model, and their assigned proximity weights. The goal of this simple model is to find the best balance between two things. First, how accurately it mimics the black box model's predictions in that local neighborhood. And second, keeping the simple model itself as straightforward and easy to understand as possible. Once this simple local model is trained, its parameters, for instance, the coefficients if it's a linear model, or the rules if it's a decision tree, directly provides the explanation for the original instance predictions. These parameters highlight which features and to what extent contributed to the black box model's decision for that particular input. All right, so now let's talk about these for deep learning models, interpretability and transparency. So first, interpretability is about understanding how a model reaches a specific prediction or decision. Deep neural networks are inherently complex, with millions of weights and multiple nonlinear activation layers, hierarchical abstractions, so on and so forth. So you can't simply inspect them like you would a linear model. Instead, we rely on post hoc tools, techniques like what we discussed earlier, SHAP or LIME, to compute feature level contributions. Saliency methods like integrated gradients highlights which input region the model focused on, and partial dependence plot let us visualize how changing one input affects the model output. The goal here is to give domain users and auditors insights into internal reasoning, especially in critical decision. Transparency, by contrast, is broader and deeper. Here we mean openness around every facet of the system's lifecycle, from architecture and training to data provenance and recognized limitations. Transparency covered how the model was built, which data it used, which hyperparameters were set, testing benchmarks, and non-failure modes. This level of openness builds stakeholder trust, supports accountability, helps catch hidden biases, and is crucial for regulatory compliance. Think audit trails under EU AI Act or sector-specific ethics review boards. We often say interpretability is about making decisions inside the box visible. Transparency is about exposing the whole box, its insides, and how it was built. A system that is interpretable can still lack transparency if you don't know how it was trained or what biases it might contain. On the other hand, a transparent system without interpretability tools may still produce inscrutable predictions at runtime. The ultimate goal then is to provide full lifecycle visibility, making it easier for anyone from engineers to end users to assess, trust, and responsibly govern the model. This dual length of interpretability and transparency is essential for deploying AI in sensitive domains, from healthcare to finance to criminal justice. Now, building on this foundation, in our next slide, we will examine specific interpretability techniques for deep learning models, such as saliency maps, attendancy visualization, and also their limitation when applied in real system, and with a focus on large language model. So first, consider chain of thoughts prompting, where the model verbalizes step-by-step reasoning before outputting an answer. This technique often boosts model accuracy significantly, especially on math, logic, or multi-hop reasoning benchmarks. In fact, large transformer-based models have shown striking improvements on problems with COT prompting, sometimes surpassing fine-tuned model. However, there's a serious faithfulness concern. COT explanations may not reflect the actual internal computation of the model. Many studies demonstrate that COT traces can be rationalized, aligning with human reasoning expectations while diverging from the model's real decision path. In high-stakes domains like medical diagnosis or legal decision support, this connect can lead to misplaced trust. To address this, mechanistic interpretability techniques let us probe whether specific neurons or circuits causally contribute to certain outputs. For example, with activation patching, we systematically replace internal activations between a clean run and a corrupted run to observe effect on output. This helps identify whether internal features truly drive reasoning or are merely just superficial. So this method provides deeper transparency than COT prompting alone. They reveal the actual circuitry behind predictions, but transparency must be balanced with privacy concerns. Exposing internal activations risks leaking sensitive training data profile. Therefore, it's crucial to visualize confidence scores with COT outputs, annotate uncertainty, and refrain from over-reliance on potentially unfaithful claims. In practice, an ethical and safe UI may show a chain of thoughts explanation with a confidence meter, or highlight that the COT is likely faithful or low fidelity based on internal testing. Combining COT with mechanistic probing yields a richer, more transparent interface that is both informative and ethical sound. Here we examine two real-world human-AI interaction scenarios where explainability directly impacts outcome and trust. First, in clinical radiology applications, deep learning models often flag anomalies on CT scans, by overlaying shape or integrated gradients heat map on the scan. Clinicians can visually assess whether AI attention aligns with medically meaningful regions. Research shows this alignment can increase diagnostic confidence by approximately 20%, particularly when heat map correspond to radiologist's area of interest. From a design perspective, it's best to use a progressive disclosure UI that initially shows heat maps and then let users review more attributions detail on demand. This minimizes visual overload while still offering depth when needed. However, be aware of automation bias. Clinicians sometimes overtrust the AI focus, even if it's misaligned with their judgment. That is why it's essential to maintain human-in-the-loop control, allowing radiologists to override or challenge AI guidance as needed. Second, in the banking domain, customer service agents often rely on machine learning systems to flag suspicious transactions. Here, LAMP explanations highlighting key features like unusual merchant types, transaction size, or location mismatch helps agents understand and convey the rationale to customers. This transparency translates into better first call resolution rates or higher customer acceptance of automated blocks or holds. In both contexts, effective use of explainability tools like SHAP in radiology, LIME in fraud detection, enhances user trust and performance. But careful design is crucial. Interfaces must support clarity, optional detail, and human agency to avoid over-reliance on or misinterpretation. Now that you have seen how explanations shape human decision-making, let's proceed to explore the ethical drivers and risk frameworks guiding the responsible use of these techniques. Let's unpack the ethical drivers and risk themes motivating the need for XAI in sensitive domains like healthcare, finance, or criminal justice. First, bias with visibility. One of the most important roles of explainability tools like SHAP or LAMP is to expose when models rely on processes such as zip code, income levels, or education. Features that correlate with protected attributes like race. Research show that these processes can lead to unfair outcomes even when direct demographics features are excluded. Identifying these proxy signals by explanation is a first step towards mitigation. Second, transparency and accountability are built into audit trails, not just the surface level visualization. By logging explanation data, organizations can reconstruct model decisions when challenged, satisfying regulatory requirements, and enable external or internal reviews. This is particularly important for high-stake decisions where auditors or impacted individuals may request rationale. Third, we must face the trap that a visually appealing explanation doesn't guarantee actual causes. Studies on automation bias warn that human may over-rely on beautifully rendered explainability plots, discounting contrary evidence from domain experts. This is the fourth sense of security problem. Explanation may be misleading, if not faithful to the model's reasoning. Force bias detection is not a one-time event. It requires ongoing auditing. For example, subgroup performance checks and fairness metrics after each model iteration or data drift. Policies in employment and finance increasingly mandate such bias audits to detect emergence disparities over time. In sum, explainability enables us to detect hidden unfairness, enforce accountability with audits-ready logs, guard against overtrust through education and interface design, and ensure fairness through regular audits and monitoring. This slide tackles the global regulatory environment that is making explainability not just best practice, but mandatory in many contexts. First, the EU AI Act, which took full effect on August 2024, categorized AI systems into risk levels. High-risk systems, those used in loan decisions, hiring, health diagnostics, and policing, are subject to steep transparency and risk obligations. Providers must furnish detailed documentation, including accessible explanations for individual decisions, model design, testing, data sourcing, and risk containment strategies, such as human oversight and post-market monitoring. In the US, the Treasury issued guidance emphasizing that financial institutions should implement interpretable models to support lending, credit scoring, and risk decisions. These models need to be explainable, not just accurate, because they directly impact customers' lives, and regulators expect transparency in automated decision-making process. In FDA's 2025 draft guidance for AI-enabled medical devices requiring developers to provide human-readable rationales for model methods and decisions. The guidance also called for early engagement with regulators, life cycle monitoring plans, bias evaluation, and clear communications of AI role in clinical workflow. So these regulatory frameworks converge around a central theme. Explainability is now a legal norm for systems that significantly impact individuals. Compliance entails logging decisions and explanation artifacts, maintaining transparency around design and deployment, enabling clear rationales for each decision, and embedding human oversight and recourse mechanisms. Organizations that proactively integrate robust XAI pipelines, combining technical transparency with documentation, are not only better prepared for compliance, but also build a strong stakeholder trust and resilience across domains. Let's work through this best practice checklist to make sure your explainability pipeline is robust, user-centered, and ethical sound. Use Sharp for higher level insights like which features matter most overall, paired with local methods such as LAMP, critically run stability tests, rerun line multiple times, or test shape across subsamples to ensure results are consistent across runs and robust to data variation. Store artifacts logs and integrate explanation test into CI/CD. Persists explanation output as artifact. Sharp scores surrogate model coefficients, saliency visuals. Integrate this into the CI/CD pipeline to automatically detect drift, instability, or bias change. As a XAI-aware CI/CD processes promotes accountability, continuous observability, and audit readiness, and conducts UX studies. Technical correctness alone doesn't ensure explanation are useful. Run user research, indoctrinate clinicians, fraud analysts, or customers into interpreting the visual formats, and evaluate comprehension, usability, and decision impact. User metrics like the system causability scale to compare human and versus machine explanations. Engage governance teams clearly. In high-stake areas, such as healthcare, finance, legal, engage an ethics review board or governance council during design. Share your explanation strategy, UI mockups, and bias mitigation approaches, so potential risk can be caught and remediated before field deployment. Transparency and trust start with shared oversight. Following this checklist ensures your XAI infrastructure supports reliable insight, audits compliance, ethical oversight, and human trust. It's not sufficient to build explanations. You must validate, communicate, govern, and iterate them carefully.